So, hi everyone. Welcome back. We now have our fourth speaker for today. His name is Carlo Sferazza. Carlo is a postdoctoral researcher at UC Berkeley, working with Professor Peter Abiel. His research focuses on advancing humanoid intelligence by incorporating priors, inductive biases, and multisensory feedback. Carlo obtained his PhD from ETH Zurich in 2022 under the supervision of Professor Raffaello D'Andrea. During his doctoral research, he worked on the design of vision-based, data-driven tactile sensors and the applications of such sensors to robot control and dexterous manipulation. His PhD thesis was awarded the ETH medal, and in 2022, he was selected as an RSS pioneer. He's also the recipient of an SNSF postdoctoral fellowship, the best paper award at the 2020 International Conference on Soft Robotics, and the 2017 ETEL award. I think his research is very related to the topic of this workshop, and I'm very much looking forward to your talk.
Thank you for the kind introduction, and thanks to all organizers for inviting me. Actually, very much like the topic of the workshop, and I also like the title, which acknowledges the fact that we really have a world with an abundance of data, and I took the liberty to make an addition. This data is not only abundant, it's actually heterogeneous and very diverse. So what I mean is that we all know that interacting with the world is a multisensory experience. I think we all agree that touch, audio, smells, all senses are kind of complementary to vision. But this is not only true for humans or for animals, but it's true in robotics too. It's been shown repeatedly. And if we go back to ICRA 2019, there is this very seminal work in the group of Jeanette, actually animation was on the paper too, where that name was making sense of vision and touch. It was really about understanding what is the advantage of using the sense of touch in addition to that of vision. And there have been like a lot of papers kind of building on top of that. Most recently, Manuel Vieira CoRL from Schuren's group, where they showed like how audio data can integrate in the rich information that we get from vision about the environment. So there is a repeating pattern in these papers, and it is that of showing that we have a full model of a lot of sensors that achieve a certain performance. And in the moment you start removing some of the sensor information, the performance starts to drop. So there's kind of an agreement in the community, I would say, that more sensors help and less sensors lead to reduced performance. However, if we look at the general scheme of modern robot learning, where we try to achieve this kind of generalist robot policies that can be reused across tasks, we very rarely see the use of other observation in addition to vision. So as you all know, usually these tasks are described by language instructions. We might have even multiple views of images, and we're trying to get some actions out of it. But again, like touch, sound, other senses are never part of this scheme. So the question that I'm trying to answer with this part of the talk is really why aren't we using other sensors? I put down two reasons, and I think actually they are the most important here. One is obviously these generalist policies usually rely on large robotics datasets. And these datasets are usually containing vision, observation, language instructions, and actions. It's very hard to go beyond that because it's kind of a chicken and egg problem, right? Because we don't have adoption of other sensors in the community. It's hard to have people put these sensors on the robots when collecting data. But I have to say, like, even in the few attempts at collecting these larger multimodal datasets, there is an issue, and the fact is that vision tends to be a much denser signal than audio or touch. For example, touch is only kind of active when there is some contact, but often we have no contact in the scenes. So what happens is that when you collect these data sets, there is a huge imbalance in the data distribution, where you have a lot of signal from vision, but very little from audio or touch. So what happens is that when you train models from these data sets, what happens is that these models over-rely on vision and tend to neglect important information from the other sensors. So we're trying to address these challenges in the work I'm presenting today. It will be on-site as a collaboration with other people at Berkeley. Actually, Oyer is on the paper too, and among the organizers of this workshop. The paper is not an archive yet. It's going to be very soon as we're finishing up some stuff, but there is a QR code if you want to look at the website, and there is a link to the current version of the PDF too. We call this work fuse. The idea is really to fuse heterogeneous sensor and generalist robot policies. I'm going to explain you like the context in which we do it. We have a pre-trained generalist policy. I'm going to touch a bit more on what that is. That can be Octo, for example, for people in the field, but also other larger VLAs. The idea is that we want to fine-tune this generalist policy by using a much smaller data set of observations, including vision, touch, and audio, and described by language instructions. The idea is that maybe we can solve some tasks that are harder to solve with vision alone in a better way, with higher performance, but we also want to enable additional capabilities compared to those that can be achieved with vision alone. For example, we could prompt the policy with tactile attributes, for example, grab the object that feels coordinate. Or we could use a multimodal prompting, so prompts spanning multiple modalities with different attributes from touch, sound, and vision. If we have like some generative capabilities in our model, we could also ask the policy to generate some tactile attributes corresponding to the objects that it is feeling at the current time. I'm gonna go more in details in all these tasks, but the two main points here is like we want to improve performance on some tasks, but we also want to unlock new tasks that weren't possible otherwise. So one step back, the core of our work is a pre-trained generalist robot policy. So was that, again, like we have usually a transformer policy that takes in usually multiple tokens, could be, in the classical case, it's vision and language tokens. We usually have some readout tokens that attend to all the other modalities and are used in a action head that is usually trained by minimizing an imitation loss. The idea of this setting is that you train a very large data set and we can generalize maybe zero shot to other tasks or with some little amount of fine tuning. So the point of this work, though, is that can we actually leverage new sensor modalities in this setting while retaining the generality that we achieved during pre-training? Pre-training usually is like achieved in the order of hundreds of thousands of robot trajectories. So when I look at this kind of multimodal data sets, so that's how I pictured them. Yeah, there's this different modalities, clusters of modalities in our data sets, for example, vision, audio, and touch. What we want to do is our model needs to connect all of these. So the way we approach this is by doing something that we're very good at doing in the Bay Area, which is building bridges. And in this case, the bridge is made of language. So the idea is really have language instructions act as a glue across modalities to have our model reasoning across all of them. This is our recipe that we call Fuse. We have a multimodal transformer. This is a transformer that can be pre-trained on a subset of modalities, but then we augment with additional modalities at fine-tuning time. It's similar to what I showed before with these reader tokens that go through an action head. That's actually the main loss of our approach that minimizes, again, imitation discrepancy. But we have also two auxiliary losses, and this is actually very important in our approach. We have a contrastive loss, a generation loss. The point of these losses is really to tackle the issue I was mentioning before, the fact that often vision dominates during training. And I'm going to go more in detail into both of them, but the idea in general is that the contrastive loss makes sure that we align our observation embeddings with all possible instructions that could possibly describe them, while the language generation loss aims to make sure that the observation embeddings that we get at the output of the transformer are sufficient to reconstruct the instruction that could be related to this. So more in detail. So I think this part probably needs a bit more time to digest, but basically the contrastive loss is computed the following way. We have a readout embeddings that we obtain by attending to all modalities except language, and that are fed through this transformer. And then we use these embeddings and language embeddings to compute a clip loss for all possible combination of instructions that match this combination of modality. So in this case, like all the ones here, for example, pick the object that feels coordinated or pick the object that looks blue. This is, by the way, for example, for a blue rope. These are going to be positives, and all the other instructions in the batch are going to be negatives. So we pull together the positives, and we kind of maximize this alignment with the negatives in the batch. So that's the contrastive loss. The language generation loss requires an additional component, which is a language generation head that we add on top of our model. just used for this auxiliary loss in this case. We have, again, readout embeddings that are fed through the transformer. Here we do it for all possible subsets of modalities that we have in our datasets. For example, we could have rich images and touch. And now we get some readout embeddings, and then we have our corresponding language extraction. So what we try to do is make sure that we can generate that extraction from the readout embeddings. So this way, again, we make sure that at the output of the transformer, we have all information that we need to describe the task. So we don't ignore any of the modalities. So how do we evaluate this? The first thing, we need a data set, and we actually collect a pretty considerable sized data sets, about 30,000 trajectories. It's much smaller compared to what you have in vision language datasets. For example, the OpenX mixture that we used for training Octo in this work is about 800,000 trajectories. So this one is much smaller, but still pretty decent sized. It's about 800,000 data points in comparison, and they contain third-person wrist cameras views. We have 2 tactile sensors. These are digit vision-based tactile sensors. We have a microphone attached close to the gripper. And we have also IMU data that we don't use for these applications, but we provide them to the community for future usage. So all of this is going to be open source together and released together with the models, the code, and the results next week, most probably. So the tasks that will contain this dataset are mostly 3, all language labeled. We have like grasping and a tabletop scenario. We have a much more difficult task of grasping inside a shopping bag. You see, these are all the diversity of objects that we have. And we also have like a task where we kind of press some sound buttons. So these are buttons that have different colors and play different sound. So first thing we do is compare with the obvious baselines. So we want to compare our approach, which is fine-tuning using iRise recipe Octo-based model. We compare with fine-tuning Octo just using vision, so neglecting information from the other sensors. We also compare with training Octo with all modalities, but from scratch. This is a pretty weak baseline because Octo is a pretty large model and we have a very small data set. So to be a bit more fair, we also trained a resonant model from scratch where we use film fine-tuning for injecting the language conditioning into the policy. We see on the bottom the results, especially the last picture here is the average result. You can see that our approach performs much better than the other baselines, but this is especially true in the shopping bag task, where we have a lot of partial observable scenarios when you use vision alone. Well, the bag becomes very dark and the objects are not very visible. You can see our model in action actually at the top, where we ask the policy to grab the yellow block and you can go inside the shopping bag and take it out. And the importance of the 2 auxiliary losses that I was telling you before is actually very true for the shopping bag. We are actually twice as better in terms of success rate. By the way, the shaded color is about finding the objects, while the darker colors are about actually grasping them. And you see that in a partially observable scenario as the shopping bag, both of the auxiliary losses help. If you remove any of them, the performance drops. So these are things that somehow the vision policy could have done, but it does them in a worse way. Now, what are things that the vision policy couldn't do at all? So one thing is a zero-shot touch description, and we are using here our generative head that we actually implemented for the auxiliary loss, but it can be used also at inference time. For example, we can have the robot go inside the shopping bag, pick an object or different objects. We have some tactile readings, and then we're going to ask our generative head to generate the possible instructions for this kind of readings, and they will detect that in the first image, the object actually feels fibrous, in the second image, it feels slick. More interesting, a multimodal disambiguation. You can ask the policy to grab an object that looks yellow, but there are more yellow objects on the scene. So you can also add a tactile attributes, for example, feel squishy or feels crinkly. And the policy now has a feeling of what the tactile attributes feels like, and then it goes to the right object and pick them up. We had some other experiments that we called cross-modal compositional reasoning. The idea is really to reason across the whole range of modalities. For example, this setting here, these buttons are all present in the training set. So the policy kind of knows what color is associated with what sound. So for example, the green button would play metal. And so if you ask the policy to grab the object that is the same color as the button that plays metal, then the policy right away goes and pick up the green object. So this is kind of easy because you could say like, okay, if these are only training buttons, maybe during fine tuning, the policy just remembering that it should associate green with metal. So we took this a step further and did a more complicated cross-model compositional task in multiple steps. I'm going to play this multiple times. So if you don't get it the first time, it comes again. It's a bit subtle, but I think it's pretty important. So we're gonna try to introduce some test buttons in the scene. The blue and the red buttons were not in the training set. So what we're gonna do is first ask the policy to push the blue button. So it's gonna go there. And I hope the sound plays. So it's gonna listen to the audio. And now we're gonna ask the policy to generate the corresponding audio description using the generative head, and that tells it like push the button that plays piano. So again, it has some understanding of audio. By listening to the audio, it can reconstruct language extraction. Now we're going to take the language extraction and we're going to feed it again to the policy. And this time, the policy will interpret it as go and push the button that was seen during training that played piano. So it will remember that's the pink button. And you can listen to the piano played by the pink button. So the model really successfully correlates audio and vision, and repeating this, effectively, this is equivalent to asking the policy in multiple steps, push the training button that plays the same sound as the blue button. And we do, again, this in multiple steps. First, we go in the blue button, we listen to the audio, and then we generate the corresponding extractions, and then we look at the training buttons, and we find the one that was playing the piano. By the way, these are different pieces of the same song. So it really has an understanding of what piano means, although it's the same song. So takeaways of this project is really that general cerebral policies can actually be fine-tuned with much smaller datasets made of multisensory data. This results in better performance across some complex tasks, but also enables other tasks or capabilities like multimodal prompting. Something I haven't shown, Fuse is actually applicable to a variety of VLA backbones. These are some preliminary results. We have a much larger VLA based on polygemma models that can basically do the same things with the same recipe. And this is just some showcasing results, but in the final version of the paper, you see all of this in greater detail. Yeah, again, here's the QR code. So switching gears a little bit, we've been talking about a case where we have many sensors on a robot and what are the nice things we can do with them. But looking a bit broader and looking at more like mobile by manual manipulation, often we have many more sensors because we have vision, we have touch, but we also have joint angles, and these are often distributed across the entire body. But we also have a numerous number of actuators. We have joint commands, but we also have a lot of hand commands if you think about dexterous manipulation. Again, there is kind of a specific placement of the sensor over the entire body. So what we're asking ourselves, can we use this notion of locality to actually make the problem a bit more tractable given this high number of both sensors and actuators? So can we actually leverage locality in a transformer setting for policy learning? And if you look at transformers, they are built on this self-attention mechanism, which was designed to deal with a global relations across sequences. And these sequences are often structured like language, where the first word can be very related to the last word in a sentence and so on. While animals are a little bit different, there is this notion of spatial connectivity of the way that our neural system is routed. And that allows us to have things like shorter loops, or what we call reflex arcs, where we have some very fast reactions at the level of our spinal cord to really react very fast to interactions with the environment. So what to ask ourselves is this just an evolution artifact, or can we actually use locality as a powerful inductive bias for policy learning? That's the motivation of this work, Body Transformer, that we presented at this conference. And the idea of body transformer is to have an architecture that just biases the vanilla transformer to take into account the structure of the robot body. So in practice, what we do is we treat the robot body as a graph of sensors and actuators. So we split our observation and our actions across the nodes of this graph. Then we make sure, using masked attention, that at every node, at every layer of the encoder, every node only attends to itself and the direct neighbors. And then the next layer, we're going to do the same thing. And then our receptive field or our information grows across the graph, and the information again gets pulled to all the nodes. Finally, we decode actually the actions also locally at all of the nodes. We have two versions of this architecture. One is called BOT hard, which only uses its masked attention layers. And we have another version that would be more clear why we have it. BOT mix actually interleaves masked attention with the regular self-attention layers. The way we build these masks is the following. Here we have an embodiment graph, let's say a humanoid. We've just built an adjacency matrix out of the graph. We add ones at the diagonal because we also want to do self-attention at the nodes, not only look at the neighbors. We evaluate this in different settings. First, imitation learning. This is a pretty large imitation learning benchmark, which contains humanoid tracking motions, all action labeled. It's about 800 different motions or tasks, and they're split in a training and test set. What we've shown is that a body transformer can actually outperform the baselines, specifically transformer and NLP baselines. And the interesting thing is that this gap actually becomes larger when you look at the validation set. This benchmark, people thought it was kind of saturated because it's pretty large, and so it's quite easy or stable to train. The best results before were obtained using this multi-clip policy, which is pretty fancy structure with a recurrent neural network that estimates a latent variable describing intent. And that's fed usually to a BC pipeline. Well, what we did is just using classical BC end-to-end just with the right architecture. Another exciting thing here is that if we look at scaling this model up in terms of the number of model parameters, we can see that the transformer in red actually overfits pretty quickly, while our architecture keeps scaling nicely as long as we scale up the model. So we see a similar trend in a low data regime where usually people tend to use NLPs in imitation learning because transformers would easily overfit when you have a small number of demonstrations. And what we see instead is that our approach is either competitive or better than the NLP and consistently better than vanilla transformers. We see similar improvements also in reinforcement learning. Here things are a bit more tricky because our kind of hard constraints on the bottlenecks of our architectures are a contrasting objective compared to just achieving exploration as fast as possible. So for hard exploration problems, we noticed that it's actually beneficial to add some self-attention layers interleaved with our mask attention. So this way, the global information is pulled through the graph a bit earlier during the pipeline. And that helps in achieving the top performance on these harder exploration tasks. To demonstrate real-time applicability, we also deployed this on a real system. This is nothing fancy. It's really like a blind policy transferred from sim to real, trained simulation using reinforcement learning. Another interesting fact is actually the body transformer can achieve much better computational complexity compared to vanilla transformers, because you can imagine like there is a very big sparsity in the attention metrics, and that usually brings at least like a 2 times reduction in the computational cost compared to the vanilla attention. So some takeaways. First one, and probably the most important, is that inductive biases matter for policy learning. And that's also very true for a single embodiment. People have been trying to use graph across multiple embodiments, but actually what we're showing here is that the graph bias is actually also important when you have one single embodiment. That doesn't mean that it cannot be applied for cross-embodiment, but that's the message of the paper. The way that our inductive bias works is by leveraging physical agents as graphs of sensors and actuators. And this way, body transformer can outperform the baselines, showing a scaling trend, which is promising, and has potential for faster computation. If you're interested in this kind of problems with a lot of sensors, a lot of actuators, actually we developed the benchmark. It's called the humanoid bench. The idea of this benchmark is to have like a lot of different tasks tackling different challenges. So we really put a lot of thought in what tasks enable dealing with different challenges. We put a lot of very flexible observations. We have egocentric vision, all body tactile sensing, higher resolution of the fingers and the feet, lower resolution everywhere else with proprioception, 61 actuators, so very high degrees of freedom. It's open source, feel free to try it out, contribute to it. There is a lively community already built around it. Yeah, we're very excited about it. With this, I'd like to thank all my colleagues and collaborators on the projects I presented, and happy to take any questions.
Your audio signal, is it just audio or all the direction you can recognize where the audio signal comes from?
Yeah, no, it's a mono microphone, actually. It's just a single channel microphone, and we just build a spectrogram out of it of the last second of data. And yeah, we don't have information about direction yet.
But it's what modality sensor, which does something, especially if you stay up at night to get some water, you do not have to put on the light. You just hear of your own actions and echoes where to go. So you have a kind of audio 3D reconstruction, and you have to know where the sound comes from. So
it's a great point.
You use mono?
It's a great point, but we use an action sequence as well. And so we don't use just a single step in our policies. Our policy is conditioned to previous steps and actions. So you can kind of get a sense, depending on how your robot is moving or where the sound is coming from, looking at the sequence. We don't see it instantaneously, I agree, and you could use a stereo microphone. We just took the cheapest numbers, and that's actually the real choice.
Any more questions from the audience? Actually, I also have a question, also regarding the multimodality that you use. So I would assume that for your tactile sensor, the signal you get is very specific to that sensor that you use. I mean, for cameras, you can have different types of cameras in your data and still use them for training, even if your camera is different. How is that for tactile sensors? Can you really only use that data if you have the same sensor?
Yeah, that's a great question. I would say, like, in tactile sensing, there is the issue of heterogeneity even within the sensing modality. So if you have a completely different tactile sensors, it might be tricky, and you probably need to project things in a shared embedding space. And there are works that have tried that successfully. So there is promise there. For what regards this work, we don't use only 1-digit sensor or 2-digit sensors for data collection because sensors break during like such large data collection effort. So just the simplest way you can do this is performing background subtraction on the images so that you are in a more similar space across sensors. So that if there are some differences during fabrication, those are evened out. And then what turned out is, I think in our data sets, we have like about 6 sensors for data collection. And it turns out that then it generalizes to all other digits that we've been trying.
Maybe one other question.
Just one short. How does it correlate the tactile sensor with squeaky property with language? I didn't get that part.
Yeah, because during training, we have labels that are like made their way. We have a very large degree of labels. We do use like in language model rephrasing as well, so that we add some synonyms and so on to get like really grounded in language. And that turns out to actually help, yes.
Then thanks again to our speaker.